To today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is NDS 2018 Timber Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Choa will be joining me as well as your moderator, answering any questions you may have. They are both technical support engineers, also located in the Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. Regarding the content over the next hour today, because we're still getting familiar with the interface options in the new generation RFEM 6, I will go through the structure modeling and loading workflow within this main program. Along the way, we'll take a look at the data input for the timber design add-on. So the huge benefit of RFEM 6 is that these add-ons are now integrated within the main program, so it will be part of this modeling workflow. Finally, we'll run our calculation to take a look at the analysis, but also the design results according to the NDS 2018. And along the way, I'll be sharing a few new features that we have specific to the NDS available now within RFEM 6. So we will begin within RFEM 6 here, and when we start a new model, we want to initially give it a model name. The type of model will be 3D. Under the second tab here, we want to activate our add-ons, and today we'll be specifically working with the timber design add-on, which I've checked here. So now under this third tab, because I've activated the timber design add-on, we can select our standard, which will be the NDS, but we also see the CSA standard as well as other international standards available. Up at the top, we will be generating our load combination specific to the ASCE 7, but you'll notice that we are selecting this wood option. The program will throw up an error if you don't select wood when you have enabled the timber design add-on. Now, the same concept for the NBC as well as many of the international standards. Exact same load combinations will be generated from the ASCE 7. The difference here, though, is that we can now take into consideration creep. So I'll get into this topic a little bit later on, but that is just the main difference here of why we need to select ASCE 7 wood. We can also take into consideration these automatic load wizards for snow and wind load according to the ASCE 7. The wind load is still in development, but we'll be seeing with our first example today how we can automatically generate those snow loads on our structure. Under these settings and options, we will set our global z-axis to upward as well as our local z-axes. I have also enabled these member representatives. So when I activate this option, I get a new tab here. This allows me to group together members that are similar with cross sections, with lengths, with materials. Notice I've also enabled this comments. This will come into play later on. So we'll see the advantage of what member representatives can do for us. Finally, under the model parameters, you can see that this links directly to our online GeoZone tool. And this GeoZone tool is available on our website where we have integrated the maps from the ASCE 7 for snow, wind, tornado, and seismic. This is linked with Google Maps technology, so we just need to type in our project location, for example, Philadelphia, and we can see the ground snow load is automatically populated here directly from the standard. When I click OK, all of this information is automatically going to be imported into the model that will be used for those load wizards a little bit later on. So once we are done defining the base data, we will be brought into the main program, and we can see our drawing grid activated here. Well, we can modify those drawing grid settings by right-clicking at grid down at the bottom. My default spacing here is set at 1 foot. If we see anything other than this, for example, when you first start the model, you might see something like around 3 feet. You can always hit this default option here to go back to the 1 foot or adjust this to maybe 0.5 feet. We can also open up our units here and change this to inches if we're working on a much smaller scale. So there are many different ways to model within the program. We could begin by drawing our first member and defining the cross sections and materials as we go. But an alternative option I'm going to take is to define all of my cross sections and materials at the beginning. So over in the navigator, I can right click on my sections and I can create a new section here. I want to access my section library, and we have our standardized sections over on the left, which does include timber. So when we launch this, we can use our filters over on the left to filter the NDS 2018, and we see the various dimensional sections available to us, including glulam, for example, and we can see all of the available sizes. Now, the alternative option is to go back into the library here and choose one of our parametric massive sections. So for example, we can just choose a rectangle. This allows me to input in the dimensions directly, and we'll choose 8 inches in width and 15 inches in depth. The cross-section properties will be automatically calculated here. And back under that first tab is where we need to set our material for this cross-section. So we'll visit our material database now, and we can use our filters over on the left here to filter to timber. We can filter to the NDS 2018, and sure enough, we have every single material available here from the NDS standard. Now we can take it a step further, and perhaps we want to filter to table 5A for our glulam materials. And I'm going to select 24F 1.7E. Over on the right-hand side, we can see the different options, and we'll choose Southern Pine. I click OK, and now that material is available to me for all future sections that I will model in the program. I can simply make a copy of this existing cross-section, and rather than going into my library, I can simply type in the exact dimension here, 26. So we'll notice that this cross-section updates accordingly. Same material will be used. We want to create one more cross-section here. This time, instead of a rectangle, we'll choose a parametric square section. Under the massive tab here, I will go ahead and adjust the dimensions to 6 inches. Under the main tab, I don't want to set glulam, but rather I'm going to go back into my material library and choose table 4D. Now we can see all of the available materials to us, which is still a little overwhelming, so we can take advantage of the search options down at the bottom. So for example, if I begin to type Douglas, notice that all of the materials with Douglas within the name are now filtered. So I can choose Douglas for large north, and then I can scroll over to select number 2. I click OK, so now we have that solid section given to us here. Once I click OK, what I'll notice is that my materials and cross sections are now available within my navigator here. So I want to begin by drawing my first member. I will adjust my drawing grid into the vertical XZ plane, and I will go up to my tool to draw a new single member. The member type is going to be beam. The design properties are activated here, and this is specific to the Timber Design add-on and relative to these additional tabs up at the top. So we'll leave this enabled, but I'm not going to get into the details right now specific for the design properties. We'll go to the section tab here, and the distribution type is going to be set to linear. So this allows me to define a tapered glulam section. Now, new within RFEM 6 is that previously we only allowed you to define a tapered section that looked exactly like this, where the center line just runs right down the center. But we have added within RFEM 6 the ability to adjust the alignment. So now we can see that the taper only occurs at the bottom section of the member. So the member start will be that 8 by 15 section, but the member end will be the 8 by 26 that we've already defined. The material is automatically set here. So this is all that we need to do to define our first member. We click OK, and I can snap from the point 0, 0, 0 up to a point 15 feet in the vertical direction, and we have our first tapered member. Now, in a similar fashion, I can snap to a point here 23 feet in the X direction up to the top of the column. If I right click to exit out of that dialog box, I see here that I would like to add in some type of pitch for my roof, and I'd like this pitch to be 14 degrees. So rather than manually having to figure out the geometry, we can select this member, and under the edit options, I can go down to chamfer. And I can input in an angle of -14 degrees. I would like to rotate about the global y-axis in the vertical z direction. And then I need to graphically select my base point here. I click OK, and so now we'll have that 14-degree incline. I select both of these members, and I'm going to utilize my mirror tool. This is exactly like what we would see in something like AutoCAD, where I can create a copy. I would like to mirror about the ZY plane, and I'm going to choose my mirroring point right here at the apex. I click OK, and we should see our first frame generated. Now, I want to add a member hinge at the top here only for my beam on the left. Well, I can do so by double clicking on the member. Now, by default, everything is considered fully fixed. So in order to add in that member hinge, I can activate the hinges here. And now we get a new tab. And at the member start, I can define my member hinge. And you can see that the program automatically suggests I probably want to release the moment about the local Y and local Z axes. That's correct. I click OK. So now that member hinge definition is available to me for any future members within this model. I don't need to keep redefining. I can simply select it from this drop-down box. I can click OK. And now we should see that member hinge applied to that beam on the left. So I'll turn this into wireframe view, and I'm going to turn off my member representatives in order to make this a little bit more clear for you. I'm going to hold down my control key to select both of these top members. And I'm going to right click, and under members, I am going to divide the member by a set number of intermediate nodes. So I want to add 2 nodes along the member length here, but it's really important that I also check this option down at the bottom to create the on member nodes without actually dividing the member. We want to keep these as one continuous segment and just rather have these nodes added along the length. So when I click OK, you'll notice that these nodes are added. They're a different color than my standard nodes. If I double click on it, the reason why is because it has this special setting here. The node type is set to on member rather than standard. So now any other member that frames into this original member, maybe we add in some nodes at these, or add in some loads at these specific nodal points, will all be detected along the member length. I'm going to take my selection box and to drag from right to left. And notice I am not going to select the nodes at the bottom of the structure, and there is a reason for this. We will select all of these options except for those nodes and utilize our Move Copy tool. Move Copy tool allows me to create a copy, and I'll create 4 copies in the Y direction of 16 feet. But under my second tab, I have this option to activate these step links. So when I activate this, I get a new tab, and the program allows me to create new members between my copied nodes. So I can create a new template, and this should look like a familiar dialog box. It's as though we're drawing a new member. The member type is going to be set to truss. So truss is a little different, and you'll notice that the hinges is now grayed out. That's because internally we're going to assume that we have a moment release at the member start and the member end. So rather than having to manually define that, we can select truss, and that's automatically applied. Now for my cross section, I want to use my drop-down box here to select that 6x6 solid Douglas fir large section. I click OK. Remember, I'm still within the Move Copy dialog box. I click OK. And again, the advantage is that the program has automatically generated those members between those copied nodes. Okay, so what we would like to do now is to add some columns at the front and rear of our structure. What I'll do is turn this back to wireframe view, and I'm going to adjust my drawing grid origin with this button up here in my toolbar. And I want to snap that directly to this point along my member length. So we can see when we rotate this around, the drawing grid's still at the front of the structure, but I've just modified the location. We're going to draw a new member. The member type is beam. I do want to activate the hinges here. At the section tab, I will leave this as the 8x15 section, but not tapered, just one continuous section throughout the length. For the hinges, I would like the member hinge to be applied to the member end. Remember, I've already defined that member hinge. I can select it from my drop-down box. I click OK, and I'm just going to snap here from a point at the bottom of my structure up to the top, the intersecting node. Now, this node needs to be slightly adjusted at the bottom. Rather than sitting at negative 0.33, I want it to sit at 0 elevation. I just adjust that, I hit enter, and now that column is exactly where it should be. I can highlight this element, hold down my control key, and utilize the drag and drop feature to make a copy here on the right side of the structure. I would like to add in some additional lateral bracing here in the global X direction. So we go to draw a new member. Once again, the member type will be set to truss. The section is going to be that 6x6 solid section here. Remember, I don't need to apply any hinges because internally the truss option is taking care of that. And I'm just going to snap from the bottom of my column elements up here to the top. I can rotate this around. Notice the program automatically snaps to these nodal points. While I'm still within this dialog box, I want to add in additional lateral bracing here in the global Y direction. So I will snap from the bottom of the column. Notice the program detects the midpoint here of that truss segment. And I'll do so up here on the roof by just selecting my start and end node points. And we'll do it one more time here. I right click to exit out of this dialog box. Zoom in just to make sure everything's connected, everything looks fine. Now I'm going to hold down my control key to select these additional brace elements that I just created. We'll utilize our mirror tool once again to create a copy about the YZ plane, and I'm going to select my mirroring point at the top here of my structure. I click OK, and now we have the bracing on the other side. I would like to take these elements at the front of the structure. I will use my selection box to highlight them all. I hold down my control key, I drag and drop to make a copy at the rear of the structure. So now those column elements and braces are shown at the rear of the structure with that simple tool. Okay, the member modeling is now complete. What I would like to do is to support the structure with a new nodal support, and we can find that up here in our toolbar, assign new nodal support. Now we have some default options here within the dropdown, including a typical hinged, we have fixed, or we have a few roller options. Of course, you can always create your own nodal support option with the 6 degrees of freedom. Non-linearities are available in there as well, but for today, we're just going to choose the default hinged. I click OK, and this will allow me to highlight over all the nodes at the bottom of my structure. And if I right click to exit out of that dialog box and right click on any one of these nodal supports, I can use my slider option here to increase or decrease the size. So that's also new within RFEM 6. So our member modeling is complete. We've added the supports. I'd like to move on to loading now, but there's one thing that I want to take care of related to modeling that does affect our loading. So this will be a structure with obviously some type of roof membrane. But I don't want to actually draw in the roof surface with a material and thickness. Rather, I'm going to take advantage of a new feature within the program for load transfer only. So I'm going to draw a new surface, and the surface is not going to affect the stiffness. It does not add any rigidity to the structure. We're not applying a material. We're purely using it for load transfer to our members. So within our toolbar, we can draw a new surface, and I'll choose the option polygon. So again, rather than the stiffness type set to standard, where I would define a material and thickness, we're going to use our dropdown to select this new option, load transfer. Everything is grayed out here. Again, we're not adding stiffness, but rather we go to this second tab here and we tell the program in which direction do we want to transfer the load. Based on one-way load distribution of the x-axis, these are local x-axes of the surfaces, local y-axes, or do I want two-way load distribution in both directions? We'll go ahead and stick with only the x direction. And when I click OK, this allows me to snap to my different points here to draw in this load transfer surface on the left side. And we can see that dotted line shown there in wireframe view. We'll do so on the right-hand side, and we'll go ahead and close this loop by selecting our original point, and here are those two surfaces generated. I can right-click to show the local axis system of those surfaces, and we can just make sure that the local x-axis direction for the load distribution is in the correct orientation. I'll turn back off the local axes. We can even turn this into rendered view here if we'd like to see those surfaces in a bit more detail. So now that these surfaces are drawn, our modeling is complete and we can truly move on to the loading. So in order to apply the loading to the structure, we need to set up our load cases. I will go up here to my toolbar to select Edit Active Load Case. Now the program by default creates my first load case here, and it is called self-weight. Well, I can go ahead and rename this if I would like to dead load. Notice the self-weight is active here. The action category is based on the ASCE 7. We have selected dead load from this dropdown. I'm going to create a second load case. This will be called snow load with the action category of snow. Self-weight is unchecked here. We don't want to account for it twice. I'm going to create a third load case, which will be wind 1 with the action category of wind load. And I can even make a copy of this existing wind load case to just simply rename it to wind load 2. Now I'll get back into this dialog box to explain a little bit further about design situations, load combinations, but for now I just wanted to set up these load cases. So now that those are set up, I can actually apply the loads to the structure in the relevant load case. We'll begin with dead load. So the entire advantage of these new surface load transfer options is that I can now apply a surface load to this structure, which is going to be much more efficient than applying individual member loads to each one of my frames, for example. So I'll go up here to draw a new surface load. And the load magnitude is going to be set at negative 0.01 kips per square feet. I can graphically select here surface number 1 and surface number 2. I click OK, and here are my loads shown graphically on the structure. Now, under the display settings here in my navigator, we will see up at the very top our surfaces tree. When I expand the surfaces, we have this setting here to display the load transfer separately. So I can activate this, and now we can see the loads applied to each member based on the tributary area. So just a bit of a time saver here by utilizing these surface loads. Now for our snow load, we want to take advantage of our load wizard. If you remember, we set that up within the base data at the beginning of the presentation. So going back to my navigator here, but this time under my data tab, I'm going to scroll down and I'll see my load wizards tree. And we have available the snow loads. So I can double click on this. And what this will allow me to do is to automatically generate the snow loads according to the ASCE 7. So we want to choose the roof type for a dual pitch type of structure. Now, I just want to let you know that this load generator is only applicable for rectangular type structures. If you have anything outside of this geometry, you won't be able to use this automatic load wizard. So just keep that in mind. For today, we do fit into this geometry, so we want to graphically select here the nodes that make up the roof. So we will select the 6 exterior nodes, and I just click one by one. Once I finish that, the program automatically detects what the roof geometry is. Under the parameters tab, the program has already input my ground snow load. We have connected that to the GeoZone tool directly from our website. It inputs the 25 PSF ground snow load directly from the ASCE 7 maps. Now, of course, you can manually enter in this information as well. Now, the snow load parameters, maybe you'd want to adjust these, such as the terrain category, roof exposure, risk category. We can use our drop-down box for any one of these options. Under the load cases, we have the ability here to create both the balanced and unbalanced load cases. Now, I'm not going to create the unbalanced for today, so I'll just go ahead and uncheck them, but we will create the simple load case for balance. The program recognizes, okay, we probably want to use load case 2 here that was already set to the snow load designation. So it's populated that. Under the results tab, this is just the calculation to essentially come up with the applied area load for our snow load. So once I click OK, what we can see is that snow load applied to the structure here based on the ASCE 7. If I right click to display separately, and then I take my second step here of activating again to display the load transfer separately, we can now see those loads applied to our mainframe elements here for the automated loads. Okay, moving on to wind loads. Again, this is still in development for our automatic wind load generation according to the ASCE 7, so we'll just be applying those manually for today. Now, I'm assuming that I have an open structure here, so wind is free to move throughout the bottom of the structure. So perhaps for my simple wind load cases, I want to have one wind load with uplift and one wind load with downward pressure. Well, for load case 3 here, we will begin with a new surface load. The difference here is that I want to change this based on the local X, Y, and Z coordinates of the surface itself. So we'll leave this according to the local Z direction. I want to modify the magnitude to 0.025 kips per square feet. I select graphically surface number 1. I click OK. And then notice I'm going to hit apply and next. What this allows me to do is to remain within this dialog box, but we can see the upward wind load applied in the background here to surface number 1. Well, now I can just simply adjust the magnitude to 0.015 kips per square feet. I can graphically select surface number 2. I hit apply and next, and now we see that additional surface load applied on the second surface. Well, now I can simply switch to load case number 4, while again, still within this dialog box, I adjust my magnitude to negative 0.02 kips per square feet. I can type in surface number 1. I don't necessarily have to graphically select it. I hit apply and next, and we see that downward pressure applied to surface number 1 under load case 4. I'm going to adjust my magnitude for the last time here to negative 0.01 kips per square feet. I apply to surface number 2, and I click OK. So now all of our loads have been applied to the structure. So let us go back into the load cases and combinations dialog box here. Back under the base tab, remember we have activated the load combinations to automatically be generated according to the ASCE 7. The program does require us to choose the wood option because we have activated the timber design add-on. And the entire reason for this is the feature of creep. So let us jump back to the PowerPoint to discuss this in a bit more detail. This entire topic is new within RFEM 6, and we want to refer to the NDS 2018 section 352 for long-term loading. Well, within the code, and this section in particular, it talks about the time-dependent deformation or the creep factor K sub CR. And this factor should be applied to the long-term deflection, but not the short-term, in order to be considered for the total deflection according to equation 3.5-1, and we can see that written here. So when we automatically generate these load combinations according to the ASCE 7, in particular wood, we are going to create a third design situation. And design situations will make a little bit more sense in just a minute, but I want this to be clear that we are actually going to reference the IBC 2018, and in particular section 1604.3, in order to generate the serviceability load combinations directly from the IBC for our serviceability checks when we go ahead and run the timber design. And within these load combinations designated within this design situation, one of them will include this creep factor multiplied by our dead load. That's in order to consider creep. So a new feature here, previously we were not able to consider this creep factor. So you'll notice within the drop-down box, if we do not want to consider creep at all, we can just set this to 1.0. But otherwise we would choose the 1.5 or 2 factors here. This comes directly from the NDS standard. I always like to activate this option here, combination names according to the action category. And we will jump to the design situations. So we have 3 design situations generated, 2 directly from the ASCE7, LRFD, which is our factored load combinations, ASD, which is our unfactored load combinations. And again, this is new within the ASCE7 Wood, is we are going to create this 3rd design situation here for serviceability. If we want to click this info button, we can see directly the load cases that will be considered for the generation of the load combinations. And here is that creep factor times our dead load. All of these are active for our timber design add-on. Now for today, I am going to be doing my design according to LRFD, not ASD. Therefore, I don't need the ASD load combination. So I can just simply deactivate that here. It will just decrease the number of load combinations, which we can see here under our last tab. Here are my factored LRFD load combinations for my first design situation, and my 3rd design situation are my IBC load combinations. And here we see the 1.5, and we can toggle here to the assignment, the 1.5 creep factor multiplied by our TED load. Okay, so now that these load combinations are set up, what we can do within our drop-down box is see all of the available load combinations we were just looking at. We can view all of the loads applied to the structure, including the relevant load factors according to the ASCE7 and the IBC. So technically we are ready to run the analysis portion, but again, the huge advantage of running RFEM 6 is that these add-ons have all been integrated here within the main program. So we want to do the analysis and design workflow together. So what I'm going to do is to move into the design properties for all of these members. And if I highlight all of my members and I take a look at the edit member detail settings here within my dialog box, you can see I have members 1 through 70 selected. And we have our design properties turned on here, which activates these various settings here for design types, design configurations, and so on. Now, rather than individually setting this information, I want to take advantage now of our member representatives. So I will go back into my navigator display settings. I'll turn off my surfaces here. Let me turn on the member representatives and wireframe view. So you'll notice we have a lot of color coding going on here. Again, we have activated that within the base data, so the program has grouped together similar members with cross sections, materials, and so on. Now, I want to take these 4 members at the end, and I'm holding down my control key to select them. I am going to double click to edit, and I'm going to add a comment down here, such as end frame. Remember, I also activated the option at the beginning of the presentation so that member representatives will detect different comments. So now these 4 members are in a different member representative group than the interior members. Back under my navigator display, I can also see the color coding, and we can scroll through the different member design or member representative options here. Okay, so what is the advantage of these? Well, when I double click any one of these colored dots, so for example, we'll start off with member representative number 4. It will bring me into the member representative dialog box, and you'll notice we have these exact same tabs that we saw for each individual member. So what I can do now is to input in the design information for a group of members that I know are all going to have the same unbraced lengths, for example, the same service conditions, whatever it may be. That way I can go into the member representatives, make a change, and it will affect all of those group members rather than individually applying to each member. So let us begin here with this initial tapered members. Remember, this includes the 4 exterior girders here. Now we want to start off with the effective length. So I'll create a new effective length here. And this is my input information for stability design. So we're talking about flexural buckling, about the strong axis, the weak axis, and lateral torsional buckling. Now we want to set the information here on the second tab. But before I do, when I initially create a new effective length, notice over on the right-hand side, my members aren't populated. Well, if I initially create this definition, I click OK, and I go back into edit the same effective lengths, notice now the program says, okay, we're going to assign this to members 2, 4, 18, and 20. Why do I want to do that? Because now my picture in the lower right-hand corner will populate here. So I can see exactly which members I'm looking at in order to apply my intermediate restraints. So let me turn this to wireframe view. Now, this all has to do with K-factors, with unbraced lengths, incredibly important for design. And we have two options here. Number one is we could work with the table down here at the bottom. Perhaps we want to toggle this to absolute values, and I could just directly input in here K times L for my strong axis buckling, weak axis buckling, lateral torsional buckling. Now, alternatively, I can take advantage here of inputting in these intermediate supports graphically so that the program can calculate the K times L or the effective lengths automatically for me. What I want to do is to have the program detect the intermediate nodes along the member length. So I'm going to activate this option here, intermediate nodes, and then I'm going to use this option to select the member. I can select any one of these 4 members here. I'll just choose any one of them. And now notice the program has detected these 4 nodes along the member length. So we'll begin right here at the apex. Well, notice we only have a truss member framing in the weak axis direction. So I probably want to add this intermediate restraint here to only restrain my tapered element in the weak axis or local Y direction. For node number 2, we have a column framing up. So I'm going to assume that this element is restrained in the vertical Z direction, as well as in the weak axis direction from my truss, as well as rotation against torsion at this location. For my third node here, I'm going to assume these braces really have not much impact, so I'm only going to restrain the member in the weak axis direction. And finally, for my fourth option here, my fourth node, we're going to leave this as default in the local Z, local Y, and about the local X axes. So now these 3 segments are updated here to consider my true unbraced length. So this is how we can automatically consider that within the program by setting these intermediate restraints. So when I click OK, we can see here in wireframe view, these intermediate restraints applied internally within the member. They're not true supports like nodal supports that we initially applied at the bottoms of our columns. They're just purely used for the design. Now, we want to jump to our member representatives here, which include my 6 interior frame elements. We have a little bit of a different scenario here. So I'm going to create a new effective length. And once again, I'm going to define this effective length. I'm going to click OK and go right back in there to edit it. The reason why is because now under the second tab, I can toggle to my picture and I see my 6 members updated here within my graphical view. I want to detect those intermediate nodes. I will graphically select any one of those 6 elements. I see my 4 nodes detected here. Up at the apex, I want to restrain it in the weak axis direction only. At my second node, it is also the weak axis direction only. My third node, weak axis direction only. We have no columns framing up at the center beams here. But finally, at my fourth node, we do have a column. I'm going to assume that the program is going to restrain this in the vertical Z direction, the local Y direction, and about torsion. So we can toggle to our absolute values to see everything updated accordingly. Okay, so now that we have defined these for those 6 interior members, we can see the program update here automatically to show what's going to be used for design. So let us talk about the remainder of all of these member representatives. I'm holding down my control key to select all of them. It is all the remaining braces, the columns, and for this, we need to define a third effective length, and this one is much easier. All that we need to do here is leave this as default. These members are supported at the member start and the member end according to these default options here. No intermediate nodes detected. I click OK. We can see the program update graphically here within our view. Now, for the rest of these settings, the service conditions, if we go into the detail settings for these, are the members wet? Are they dry? What is the temperature? Is it pressure treated? We know that this is all going to affect the adjustment factors for the NDS design. The local section reductions, we can create notches in our members. So perhaps we have a notch at the member start or the member end, or internally, we can define that here with these section reductions. Now, this is only available for standard members. You wouldn't see this option for our tapered members if we went back to one of these other member representatives. The design configuration. So we have here strength, design, serviceability, and fire. So let us begin with the strength configuration. We'll go into the settings here. So just some various settings that will go into the strength design according specifically to the NDS. So for example, torsion. If we're not really wanting to design these members for torsion, the NDS is a little bit vague on torsion design. And I really just want to skip this. Well, what I can do is to set a higher ratio here, such as 0.3. So as long as my stresses for torsion are below a 0.3 ratio of the limiting the limiting torsion capacity, then we'll completely skip this check. So that's a little trick you can do here within these settings. Now we have some additional settings, including topics like the size factors, the flat use factors, and so on. Under the Stability tab, this is a new feature within RFEM 6 specific to the NDS. It is the representative dimension for tapered compression members. I'll go back to the PowerPoint to explain this in more detail. So again, a new feature here that we've added within RFEM 6. We're going to reference the NDS 2018 section 3.7.2 for tapered columns. So previously in RFEM 5, what we were doing is for any check along a tapered glulam member, we were just using the depth at that relevant X location. Well, the code doesn't exactly say that. It says to please calculate the representative dimension for the tapered column instead. And we can see equations 3.7-2 and 3.7-3 are given to us here directly from the NDS. And this all depends on the support conditions, but this is to calculate that representative dimension. So we'll use the variables here, the depth for max for the tapered section, the minimum depth here for the tapered section in order to calculate this. Now, again, this all depends on your support conditions. You'll want to refer to the NDS to review these equations in a bit more detail. But the equation preference can be set under the timber strength configuration and under that stability tab, which is exactly what we're looking at here. So I go back to the model and we can just go ahead and choose either equation. I'll stick with equation 3.7-3. Once we run our results, I'll show you exactly what this looks like and how we can now consider this according to the NDS provisions. These standard parameters, these are just going to be all of those various factors that go into play for the NDS design. We have all the default options set here, but you can go in and adjust these as well. So once we have reviewed the strength configurations, we want to take a look at our serviceability configurations. And this is quite a bit more simple. We have here our limiting deflection ratios for simply supported L/360 and cantilevers at L/180, and you can adjust those as you see fit. Fire resistance design, we won't be doing that today, but that is a possibility to also calculate according to the NDS standard. I'll just go ahead and clear out this setting for now, that's fine. The design supports and deflection. So by default, the program is automatically going to consider every member as simply supported. So it's going to refer back to that L/360 design ratio. Now, if you have a cantilever, you will need to define a design support, the member start or member end. I am actually going to breeze through this tab here because our second quick example at the end of the presentation today will go much more into detail for this. So for now, we just want to keep everything as default. Okay, so once all of these settings have been defined, we are now ready to run our analysis, but also the design of the structure. So what we'll do is to utilize our table options down here to drop down to timber design. So this is active because remember at the very beginning of the presentation, again, I've enabled that timber design add-on. And if I take a look at my table settings here and this first tab, design situations, I have my 3 design situations that were generated automatically from the program. We've already reviewed these, my LRFD, ASD, and then I have my serviceability from the IBC. Well, I'm not doing ASD design today, so I'll just simply uncheck that. Now notice my factored load combinations or my LRFD design situations should be associated here with my strength limit state design. So I can make sure that that is selected appropriately from my drop-down box here. I'm not doing ASD design, so we'll skip over that. And finally, my third design situation here for serviceability should be set according to the serviceability limit state design. Now the program knows which load combinations to refer to for my actual design portion of the calculation. Now, if we wanted to run fire design, perhaps we go back into that load cases and combinations. We make a copy here of maybe our LRFD design situation, and we can select fire design from our drop-down box here. Under the objects to design, we see members 1 through 70 are automatically selected. All of our member representatives are already selected here. Everything was defined for our design input for each one of those members, so we should be able to design all of them as well. I'm now ready to run my calculation, which I can do so directly within this table. So I begin the calculation and the program must inevitably run through all of my various load combinations in order to determine the internal forces, the stresses. You can see that these solve pretty quick now in RFEM 6, and we're now running the timber design add-on according to the NDS standard, and here we are presented with our results. So I'm now looking still within the table format for my timber design here, but now I have available the design ratios such as for the member representatives. Well, down at the bottom, I can select the design ratios by member representatives here. And as you can see, the program is synced up with the graphical view so that we're showing you every check within the NDS. For this group of member representatives, the program will point you to exactly where the controlling internal force or stress is located. If we're interested in filtering to only the max design ratio, we can take advantage of the filter options up here at the top. So perhaps we want to choose the option max, and now maybe we're not so overwhelmed that we can just see what's exactly controlling for each member representative. So going back to the details here within our design, I want to take a look at one of these checks. So we can see the member that we're currently looking at, one of these columns, and stability for compression parallel to the grain. Well, we've added within RFEM 6 the ability to check out the design check details. And I think this is incredibly powerful because now we are showing you all variables. We are going to show you all of the equations here and also the code references directly to the NDS standard. All this comes into play to determine eventually what is our design ratio here at the bottom. So incredibly transparent, we can understand where all of those numbers are coming from. We can add this information to our printout report. We can use our drop-down box over here to maybe move to a different section proof here to view the details. But remember, we talked about in the PowerPoint the representative section dimension for those tapered members. So here are our results now for that new check. We can see the representative depth for the tapered column is now calculated. When I click here, the program automatically highlights which equation is being used, and we can come up with that new depth that will be used for the calculations in stability. So just wanted to point that out. That was exactly what we just reviewed within the PowerPoint. Okay, so now that we have reviewed all of the timber design, of course, there's much more to look at, but for the sake of time, we'll just give you a brief overview for today. Now, I want to back this up a step. So let's take a look at only one of our frame elements here, and maybe we choose the visibility by the selected object. So we don't necessarily have to view the entire structure at once. I'm still looking at my timber design. And to briefly mention as well, everything's available to me graphically. If we go back into our navigator, we can see within our dropdown, we are viewing the timber design results. So perhaps we want to turn off the max design ratio and only turn on the serviceability for this particular frame. Or maybe we want to turn that off and we want to take a look at the stability checks. So we can toggle those on and off. We can add them to our printout report as well. But in addition to the timber design, we also have this drop-down box for the static analysis. So the static analysis was required to determine those internal forces, the stresses, deflections, and so on. Notice my table automatically syncs up here to drop me to the static analysis, and my results can be viewed in table format. So for example, I'm currently looking at the deformation, but maybe I'm interested in the internal forces of the members. So I can see my axial forces here, my shear forces, maybe my bending moments. And for any one of these members, I can right click, and under the members option, I can take a look at my results diagram. The results diagram allows me to turn on and off these various internal forces, deformations. I can view in a bit more detail what's going on along the member length. I can toggle to different load combinations here. I can add this to my printout report. I also can drag this over to my second monitor and continue working concurrently within the program. So I think it's important to know, again, that both the static and analysis design workflow is working together within RFEM 6, and both of those results are available to us. Okay, so that will summarize essentially timber member design for the most part of this entire structure, but I did want to talk about one more new feature, and I think that this is best described with a new model, just so we can simplify a little bit here. So I'll open up this already saved model, and we can see that we have multiple members drawn here. And we have our main girder element spanning in the global y-axis direction. Then I have these additional joist members, and these joists are actually going to be supported by the girder member. So they're technically going to be placed at the top of this member. When we turn this into wireframe view, we know that with any FEA program, these members are just represented by a single center line. Of course, we can render it just to get a better feel of what dimensions are being used, how these members frame in together. But underneath the hood, this is what's going on. So if my joists are sitting on top of this girder, sure, I could add in an eccentricity to move these joists up to the top, but sometimes this causes unwanted moments at our member end. So for today's example, we're just going to leave this exactly as it's shown, but just visually know that we want these joists to be framing in at the top of this girder supported by it. So what is the entire purpose of this example? Well, now we want to turn to a topic that again is new within RFEM 6, and it is compression design with stresses perpendicular to the grain. So I'm going to highlight all of my joist elements here, and I can double click. Now, again, we could take advantage of our member representatives in order to set these detail settings. Or for my simple example today, I'll just set each one of them individually, so members 1 through 6. Now we're going to go back to the design support and deflection tab that I mentioned in the last example I was just quickly going over. So what is the importance of this tab other than just simple deflection? I'll go back to the PowerPoint here so we can talk about compression perpendicular to the grain. And we'll be referring to the NDS 2018 section 3.10.2, bearing perpendicular to the grain. So what are we talking about exactly here? Well, we can refer to this picture in the lower right-hand corner. We know that the grain is going to be running parallel to the member length here, indicated by this green arrow. Well, this member may be sitting on some type of support, and the support is shown in red, and inevitably we're going to see a support force acting on the member, or this stress perpendicular to the grain. Now, similarly, in our example today, not only do we have this situation, but we also have the joist sitting on top of the girder with a force acting downward, but it's still a stress perpendicular to the grain. Well, previously in RFEM 5, we did not do this check. And the reason is simple, is that the bearing area was not known. If you remember back to the wireframe view, all that we know are these simple line elements framing in together within the FEA analysis. But now within RFEM 6, we have the ability to do this check because we have the new feature under the design supports. So you want to refer to the NDS section 4.2.6 because it is important here that we consider the reference design compression values perpendicular to the grain depending on the member's material. And the NDS has done some various studies to limit the deformation of these members and materials to 0.04 inches to come up with the design compression value. Well, alternatively, if you want a little bit of a less deformation, so let's say 0.02 inches, the code goes on to say, we'll use 73% of the 0.04 inch design value. This is important because we do need to select this option in just a minute within the program. So definitely refer to the NDS, which might make a little bit more sense, section 4.2.6 on exactly what these settings are. But ultimately, we are going to give you this check now in the NDS design results, and we will calculate the compression force. Remember, that's that red force here to the design value ratio that the member can handle. So let us go back to the RFEM model to discuss this in more detail under the design supports and deflection. So we want to take a look at our member here, and we want to assign a design support for these joists at the member start and the member end because it is resting on this girder. So we'll define a new design support definition here, and I can actually rename it just to make sure I keep all of these straight. We'll call this one joist 3 inches. It will be a direct support with the support length of 3 inches. It is going to be on the bottom negative z-axis side of the member. And again, related to the PowerPoint, this is where we need to select that compression design value, 0.04 inch deformation limit or 0.02 inch deformation limit. These supports will be considered in the deflection design. I will go ahead and make a copy of this one, and we're going to rename this one to joist 6 inches, and we're going to set the support length to 6 inches. So when I click OK, this allows me to define at my member start that 3-inch support, and we can see this in the background. It will be applicable to these supports over on the left. And then for my support on the right-hand side where it's resting on this girder, we want to select the joist 6 inches. And we can see those supports shown here graphically. Now notice everything is framing in at the center line. If we wanted to, under the main tab, we could activate here the end modifications and we get an additional tab available to us. So what is the advantage here of the end modifications? Well, if we wanted to graphically extend the member to the edge of the support, we could do so with a quick click of a button here. Now, this does not affect the analysis, the stiffness, the design whatsoever. It's purely for graphical representation. So maybe it's important that you add this to your printout report and you want to show that the member goes all the way to the end of the design support. But just know that internally, we're treating everything with the center lines. Okay, so now that we have defined the supports for our joists, we can click OK, and we should graphically see them now at the bottom of our joists here back within the main program. Now we want to do the exact same thing for our girder element. I'll jump here to design supports and deflection. I create a new design support definition. This one will be girder, and it will be 5 inches with the support length of 5 inches. So this is going to be applied at the member start and the member end. Now I want to create a copy of this one, and we will call this one girder 6 inches. The difference here, not only the support length set to 6 inches, but we want to set this on the positive Z-axis of the member, as well as activate the inner support. This is where the joists are going to be bearing down at the top side of the member instead. So when I click OK, what we can do here is to select the girder 5 inches, and this will be applied at the member start and the member end here where we have those nodal supports. Girder 5 inches, girder 5 inches, and then in my interior nodes, which we can see along the member length here, we want to select that defined girder 6 inches. If I hit my down arrow key and F8 on the keyboard, the program will automatically copy the cell before it for each one of those settings. And now we get a better visual representation here of those joists sitting on top of the girder. But we have one small problem here. Notice that this tab is also used for deflection checks. And now the program's automatically assuming that my deflection should be checked with my L/360 ratio between each 4-foot segment, and that's incorrect. We want the member to refer to the full member length for the deflection design. So how do we fix this? Well, let's go back into the edit settings here for this last girder 6-inch design support. And what I can do is to simply uncheck this option down at the bottom to consider the support in the deflection design. Alternatively, if we're thinking, okay, we do want to consider the support for the deflection design, but I don't want to check compression. Well, what we can do is to activate this here and uncheck the direct support instead. So if we don't want to have those compression checks according to the NDS, just go ahead and uncheck the direct support. But in this situation, we just don't want it to be considered for deflection design. Notice our table updates automatically here to the full member length of 24 feet. I click OK, and now we can see these design supports shown along the girder. Now, if I want, I can select this element and view the visibility by the selected objects, right-click to go ahead and hide the objects in the background. This gives us a better representation visually of those joists sitting along the member, as well as our supports. Okay, so now that we have defined these design supports, let us quickly run the calculation in the timber design. And I only want to point out what the design calculation details look like for this new check within RFEM 6. So again, I'm looking at here, my design ratios by member representatives. Doesn't matter, that's fine. I'm looking at design ratios by member representatives tab down at the bottom. And currently we're looking at the compression perpendicular to the grain according to 310.2. So again, this is that new check here. Well, before we look at the details of this particular check, let's back up a step to go to the static analysis. And this is just going to show me here my support reaction for the static analysis at this particular location. And we can see that is 2.35 kips. Well, if I toggle back to my timber design and I take a look at my compression perpendicular to the grain at this location, and I go into my design check details here, sure enough, the compression force perpendicular to the grain that the member must resist is that 2.35 kips for my support reaction. We look at the additional details here. We can see the bearing length of the design support is set at 5 inches. If you remember, I had manually input that in with the design support. The program multiplies that by the member width, the 6 inches, ultimately to get the bearing area here of 0.21 square feet. So now we can run this calculation check for the compression perpendicular to the grain to get our design ratio of 0.07. So again, this is new within RFEM 6 and it's only available when you define those design supports. If we take a look just a little further down the member here, we're also going to see compression perpendicular grain, but this time for the positive z-axis. Well, this is those joists framing down at the top of the member. So we'll go ahead and check that similar check here, but rather at the internal point of the member. All right, so that will wrap up our examples today, and we'll go ahead and conclude today's webinar. I encourage everyone to visit our website at duluwell.com to learn more about RFEM 6 and the Timber Design add-on. This webinar will be recorded and posted on the webpage that you registered for the webinar. You can download these same models that I used in the presentation. You can open them up in the 90-day trial version, which is full capability, includes all of these add-ons. If you have any questions about today's presentation or anything else, feel free to contact us at our Philadelphia office, which you can see down here, the bottom of the page. Our phone number is 267-702-2815, and our email is info-us@duluwell.com. We will have many more upcoming webinars as we continue to introduce all these new features within RFEM 6. You can register at duluwell.com under support and learning webinars. As most of you know, I tend to send out an email about a week or so before these take place, so feel free to keep an eye out for those and to register directly through the email. PDH certificates will automatically be emailed to all participants. So these will be emailed within the next day or so. It's not automatic right after the presentation to everybody who is here for the full presentation. So the full 60 minutes, this is a requirement of the states that we are pre-approved providers. If you watch the presentation with a colleague, or maybe you watched in a conference room type setting and you're also wanting PDH, but you yourself did not register with your own name and your own email, you will need to request that PDH at our email info-us@duluwell.com. So again, if you did not register for the webinar, but you were here for the full presentation, go ahead and send us an email. Let us know who you watched it with, and we will generate that PDH certificate for you. And with that said, I want to thank everyone for attending today. And as always, we hope to see you at the next presentation. Thank you.